going to run over to the expiratory limb, and then your auto selector. This is the valve. This is your handle that switches the machine from manual to ventilator. Okay, so from spontaneous to ventilated. So that's what this is here, telling the machine to turn on. All right, this is our switch. This is how we work. Switching from auto, which means turn the ventilator on, to manual. All right, so that is this one right here. Okay. All right, this is your scavenger system. So as you exhale, this has nothing to do with the inspiratory side. As you exhale, it's going to come through this black hose right here. This is going to be attached to your the bottom of your CO2 canister. It's going to come through here, come into this holding chamber, be exhaled through the waste system. So all of our scavengers are active systems. We're going to use there's two types of scavengers. We'll talk more about this too. But two types of scavengers, passive and active. We use an active system on all of them. So they're always connected to the wall source, always being pulled out by the hospital system, and they go someplace else other than the OR. Okay? Okay, and if we talk about unidirectional flutter valves at all, they're always unidirectional. All right? If they were bidirectional, then that means they're broken. If you go to perform a anesthesia machine check, you squeeze on the bag, and you don't get your expected result, you always look at your valves. These things can crack, like I said. This is the internal components. And although it looks fairly busy, there's not a lot to it. All right, there's actually not a lot to this machine. Over on this side, you've got your high pressure system, which is your O2 cylinders. So if you hear high pressure, you need to think cylinders, right? High pressure, your O2, 2200 psi. What do you think your wall pressure is? About 50. Okay, so 50 psi. So that would be an intermediate pressure system. So if you ever ask a question about a high pressure system, it's always going to be your cylinders. Okay, now our machines, they could handle that type of pressure, but as soon as that cylinder is hooked up into our machine, it immediately regulates. So we're going to have a regulator on there, a pressure regulator that's going to drop that pressure down to more of that intermediate pressure, around 50. All right, so this valve right here, it's there just directly on the other of your cylinder. As soon as you hook that cylinder up, there's a valve that sits just inside the machine. You can't see it. It's hidden in the body of the machine, but a valve is present. So anytime that you have a valve present to reduce, a pressure reducing valve, the goal is that it just prevents a lot of turbulent flow from happening. Because if you allowed that force to go throughout the machine, you're going to get turbulent flow at all levels that there's turns, at all levels that it goes. You definitely don't want that sort of pressure running through your vaporizer, and you, of course, don't want that type of pressure getting to your patient. So on the oxygen side, we have two pressure regulators. All right, the first pressure regulator is here, which reduces the PSI from about 2200 on a full E cylinder down to 50. And then the second one is right here. So this pressure regulator on nitrous and on oxygen sets in the internal housing just beneath the flow meters. All right, so when you look at that picture and you see the flow meter, your second pressure regulator is just before you turn your flow meter on. Okay, and that's going to drop the pressure down to about 24 psi for nitrous and 16 psi for oxygen. You don't have to write that down. I've got all that in slides later. But now you're at a very tolerable, acceptable psi. So as you turn your flow meter up, if you turned it up to 15, which is wide open, that psi is not going to go in and really hurt a patient. All right. But if you were running it at 50 psi, that can cause problems. If you're running at 2200, but you just blew your whole patient up, I mean, literally, their chest would probably explode. So anyway, these pressure regulators serve to drop the PSI down to acceptable levels so you don't get a lot of turbulent flow that goes on. All right, so the only thing we've looked at so far, 2 pressure regulators for oxygen, 1 pressure regulator for nitrous. Okay? Now this thing right here is called a fail-safe valve. The fail-safe valve is present to ensure that hypoxia cannot occur when you're administering multiple agents. So if you're administering oxygen and nitrous, you have them both turned on. You don't want nitrous to be able to run at 100%, or else you're going to have a dead patient. All right, so there's 2 ways to prevent that. One is internally with this valve right here, called the fail-safe valve. This thing works on pressure. So as pressure comes through this tube here, doesn't matter what the pressure's from, it's running at about 50 psi now. It's going to come in, and from the bottom up, it's going to help push this valve up. Okay, so this diaphragm right here on this valve is elevated. And when this is elevated, it's going to allow nitrous to come and seep in. And so they'll combine right here. Right? Now, if the PSI of oxygen falls down, so if we go from 50 now down below 30, 30 is the cutoff point for this, and this thing cannot open if the PSI pushing up on it's less than 30. Therefore, it will shut all nitrous off. You cannot get nitrous at that point, period. If your wall pressure falls or if your cylinder runs out, it's going to cut nitrous off. If your internal pressure of oxygen falls less than 30. All right? So you understand how that works? It comes in, oxygen's going to push this diaphragm up, it's going to compress this valve, and that allows nitrous to flow out. Now, you don't see anything for air here, but on some of the diagrams, you'll actually see a third component here. You'll see air cylinders. And the reason they don't show that is because the only thing you're going to see is 1 pressure-reducing valve for that. Okay? So you're going to see a pressure-reducing valve, but you don't see a fail-safe valve because why do you think you don't have a fail-safe valve for air? Air doesn't kill people. Exactly. You can't give a hypoxic mixture with air. So you used to have fail-safe valves on everything except oxygen, but you don't any longer because now they know you can't kill people with air, and air is used on the newer machines to drive the bellows. And if you had a fail-safe valve preventing that, then only oxygen would have to be utilized to move your bellows up and down, okay? So it's a cost-saving feature as well. Air is cheaper than 100% O2. Okay, so now we come along. As I said, this pressure regulator here, this is pressure regulator number 1 for nitrous, number 2 for oxygen. This thing comes in just below, just beneath your flow meters. So your flow meters, the dials that you turn on, you start the flow of oxygen and nitrous. Now, the other important thing to see here is that where oxygen sets. Oxygen is always going to set nearest the vaporizer. And why do you think that is? Because these components here can break. They're made out of glass. They could crack. Anything could happen to them. And you want oxygen to be nearest the patient all the time. If you were to get a crack, if this were oxygen here, and you were to get a crack in this system here, then the oxygen is going to come and shoot out. You remember that Bernoulli's principle, the Venturi effect? It's going to, whenever you have a pressurized system, it's going to shoot out at a very rapid velocity through a narrow margin or through a crack. So if you have a crack here, it's going to suck the oxygen out, all right? And then you're going to get a less than the O2 that you were desiring going to the patient. Okay, so it's always placed here now. On all the anesthesia machines since the 90s, O2 is always placed nearest the vaporizer. Okay, then here's your vaporizers. So what gases are traveling through the vaporizers? Yeah, but what gases? Is just oxygen, or is oxygen and nitrous, just air, what? All of them. Yeah, so all of them, they combine here, all right? So they combine there in a common gas manifold. They're going to go through the vaporizers, and we'll talk about vaporizers next week. And then they travel to the patient. They They enter into the inspiratory limb, and they're going to find their way to the patient at that point. There's one other safety feature here called a pressure relief valve, where it's just a safety feature where if you accidentally give too much pressure to a patient, or you close the expiratory side with your APL valve, you close the valve. That's an APL valve is an automatic or adjustable pressure limiting valve. We can control that. So you close that, the patient cannot exhale anymore, we forget about it, the balloon blows up really big, pressure in the lungs are huge. This valve can kick in at that point. Once it reaches a certain pressure, that valve will open up and it will allow the patient to exhale through the inspiratory side. Okay, so that's just this is another safety feature here. All right, now patient breathes, exhales, comes through. Now it's going to go back into the expiratory side, which will include your ventilator. So on the expiratory side, that's where you're going to have your bellows, and that's where you're going to have your reservoir bag and your scavenging system. Okay? So here's your pathway of how gases travel. So I would definitely get to know the way your gases travel. Everything I'm telling you today is practical stuff it's all relevant to what we do every day, and it's definitely highly it's testable stuff. Okay, so you need to know how machines work and how they can fail. All right, so I just explained all of this, so I don't really need to read it again. All right, so make sure you look back over it. All right, because it's just the explanation. Okay, so here I've just divided the three systems. You have a high pressure, an intermediate pressure, and a low pressure system. The high pressure, as I said before, are your cylinders. Your cylinders before they get to your first pressure regulator. Your intermediate, that's where you have reduced pressure from your cylinder into the intermediate pressure, which is going to be around 50. All right? Then from that 50, it's reduced further down to that 24 and 16. And that's your low pressure. Okay, so that's what could actually be delivered to the patient. Okay? All right. So when you look at your board-on pressure gauges here, you see your pipeline and cylinder pressures. This tells you which one's high and which one's low. Your high pressure is always going to be the cylinders. Your cylinders over here. Look, I got them. I typed them in wrong. I typed them in wrong. So high pressure is here with cylinder. So cylinder about 2100 today on our E-cylinder on our machine. That's high pressure. Over here, our wall line pressure is around 50. Okay, and that's what is expected. You want around 50. All right. So make sure you reverse that. Okay. Cylinder's always high. Pressure pipeline is always intermediate. Yes? Yeah, high pressure is your cylinder. Intermediate pressure is your pipeline. Okay, so I put these on here to show how the pressures vary. Here, your nitrous, 745, right? Full tank. So right now, if you walk next door to a sim lab, our E-cylinder shows 745, full tank, and our pipeline pressure shows 50. Our air, currently, our air cylinder shows a pressure of around 1250. Our pipeline pressure, 50. Our O2 cylinder, high pressure, 2100. Our pipeline pressure, 50. So consistently, we see across the board, 50. All right. So that shows intermediate pressure, and that will be reduced just before your flow meters. All right. So here, I've divided up all the components of the machine and put them into the three systems. All right, so now we'll talk about each of these individually. Okay. All right, so talked a little bit about, I gave an overview, so we've already talked about the fail-safe valve. All right, so the high pressure system. All right, so when you get that pressure from the tank itself, if we bring it in here, it's going to have a pressure of 2200. When we go hanging that up on the side of the anesthesia machine, it's hung on something called a hanger yoke. All right. So the hanger yoke is the metal device that's going to hold it. So that's the housing for it. And that hanger yoke, you're going to have the back side of it, which has a screw. All right. So it's going to have the screw that pushes it into the pin index safety system. All right. On the machine itself, you're going to have a check valve. So it's like a unidirectional valve which prevents flow from coming back out, all right, of the machine. You're going to have your pressure indicator gauge, which is your pressure gauge, and then your pressure reducing device, which is directly inside of your check valve. All right, so directly inside you get your pressure reducer. All right, so we don't use the high pressure system unless the pipeline is shut off for some reason. Okay, so we rarely ever have to turn it on. But if you get a house system-wide shutdown, if you get a power failure, then immediately we turn on our cylinders and disconnect your house line. You're supposed to disconnect it, even though they all have one-way valves in it to prevent a backflow. You shouldn't ever trust those, right? So we want to ensure our patient gets adequate oxygenation. So house failure happens, power goes out, remove your house pipeline supply, it's just disconnect it from the back of the machine, open your cylinder up, then you got 2200 psi filling up the tank, or your anesthesia machine, you got 660 liters of O2 at that point. That's why we like to keep them near full, okay, because you never know. We've had power outages here recently. I mean, you never know how long it's going to last. Okay, so the four components right here: hanger yoke, check valve, pressure cylinder indicator, which is just your gauge, and then your pressure regulator. Okay, so this is your cylinder yoke. All right, just the housing of it. You got your screw back here that pushes it in. All right, right here is going to be the valve, and just inside that valve is your pressure reducer. Okay, so just a explanation of the different components, if you're interested in that. All right, so here's your pin index safety system in this Bodox seal. This Bodox seal, this thing is made out of a non-combustible metal, because you know adiabatic changes happen at this site. So what's important about this is that they make it out of a non-combustible material because we tend to do this. We grab the cylinders with our bare hands, including the stem of the cylinder. Our hands have oil on them. That oil is combustible, and we're never supposed to touch the stem where it connects to the of the cylinder, where it connects to our anesthesia machine, barehanded. All right, but they know that we do. Therefore, they put a seal on there that's made out of non-combustible material. But just FYI, for safety purposes, you shouldn't handle the cylinders without wearing gloves, because you will at times reach up and grab that stem and transfer your oil from your hand to it, and that can cause a fire. All right. Okay. And one important thing here, the yoke should never be left vacant. Okay, so this is a yoke. Would this be acceptable to leave? So I just said, no, yoke should never be left vacant. All right, so we'll talk about that next. All right, so on all the anesthesia machines, they should have this this little thing here. This what's that thing called? A yoke plug. Anyway, they should all have yoke plugs attached via chains on every single housing. All right, so you should have these devices present, and they need to be placed on. I guarantee you're going to see many machines that don't have them placed, but they should be. Okay, if they're not, then small amounts of air can consistently leak out, and you can lose your cylinder pressure over time. Or with nitrous, they can leak out and pollute the OR. All right, so we're supposed to put those on. So make sure that you keep those on. So just because they're not on is an excuse for you not putting them on. Okay. All right. So they're there to prevent loss. Okay. All right. It's just a very thorough description of what this yoke block is. Okay. So here on our machine, you see we do have it attached via this chain. It just hangs off the back of each yoke, and we do have it currently plugged up, so that will prevent our nitrous and our O2 from leaking out. But each single yoke must have that, not one for the machine. Every single yoke needs to have that. All right. All right. So our pressure reducing devices. I don't have to say a lot more about them other than you do need to know O2 has 2, nitrous has 1, and you need to know what they reduce the pressures to. So know the pressures of your cylinders, and then know the pressure of your intermediate pressure, and know the pressure in the low system as well. Okay? Okay. Any question about the pressures? That's going to be on the test, guaranteed. That'll be on every test for the rest of your life. Yes? Mm-hmm. Yep. So I just said that there was one, right? So anytime that you're reducing pressure from many hundreds of PSI, you do have to have 2. So I apologize. The first one is on the inside, and I actually just confused you with that. But I showed you on the cylinder that they have a pressure reducer just inside the check valve, right? So on every single cylinder, they have to reduce pressure immediately as it enters the system. 745 PSI is still a huge amount. So it has to be reduced to 50 to enter into the intermediate system. There's nothing that can go to the low system of that 14 to 26 without being at 50 first. All right, so it has to be at 50. So apologize for that. So yeah. The one that I was, let's see, right here. Okay. Okay, so let's move on. Okay, so we're right here. Know what your pressures are reduced from, and that's good. So on all the wall pressures, all your pipeline pressures, all of them are 50. So air, nitrous, oxygen, all are intermediate pressures. They're all the same at 50. All right, make sure that your cylinders are always kept closed. All right, you only open the cylinders in the morning as you're doing your machine check. And once it pressurizes the system, it's going to pressurize that high pressure system. It's going to immediately read on the on your board-on pressure gauge at whatever it is, 2200 for oxygen, 745 for nitrous. It's going to stay that way for the rest of the day. Right? They don't leak out quickly. Within the next 24 hours, it's probably going to be somewhat reduced. So at the beginning of every day, you go in, you turn it on. Turn it on to the left, righty-tighty, lefty-loosey. So turn it on to the left, open the cylinder. You only leave it open for about 3 seconds or so. You'll hear it. It'll go whoosh. That's all. Once you hear that whoosh, it has pressurized that high-pressure system. It's went up to the gauge, and it stopped. And at that point, that gauge pressure is good for the rest of the day. So you don't do it every time you have a new patient come into the room. You just do it once a day. All right? But we always need to check that, and people don't check it routinely. I can guarantee you lots of people forget to check this in the mornings. And there's some people that have big pet peeves about this, and it's something that they'll always check. I can guarantee you I always check that. As soon as I walk in the room, I look at the pressure gauge just to see if they've been checked. Now, the new machines, the completely computerized machines, we have some of them. Those things are really awesome. They can be intimidating the first time you see them. The older machines are actually, they look really simple, and they are. You've got everything you need sitting right there, but it's not a computer. The computer, you've got to push buttons and everything to turn everything on, including the ventilator. All right? With those new machines, they do everything on its own. So you're not going to come in and turn cylinders on in the morning and then turn them off. You always leave them on. It checks everything for you, and it ensures it does everything, literally. You push a button, it says machine check. All right? And it will even tell you what to do and show you pictures of how to do it. So it's anesthesia for dummies with those people. Okay. The battery life, I think it's usually about 30 minutes. So they're not very long. They do take a lot of power, and you only have battery backups on the new computerized machines. Our older machines, they don't have internal battery backups. Okay. So the Apollo is one that we have that's completely computered. It's a completely computerized machine. You will get to use those, and if the power goes out, you'll still have access to the machine. And 30 minutes is usually plenty of time to get more power. You know, you usually only need seconds to switch over from the regular house supply to emergency power. And emergency power always has to come on. I think the rule is within 5 seconds. Emergency power must come on. So you're not talking about any real length of time. Yes. Say again? Yes. Yeah, the computer, they all have an internal battery backup. It's going to last, I believe it's around 30 minutes for the Apollo. That's with it turned on, fully functional. And anyway, you shouldn't really ever have to use that, though. It'll switch on immediately, so the machine will never come off if your power goes out on the main supply until it switches over to the emergency backup. All right? So just keep that in mind also. Where is your anesthesia machine plugged in? Is it plugged into the white outlet or to the red outlet? If it's plugged into the red outlet, you should really never lose power except for possibly 5 seconds until it switches over. Okay? Then the generators kick on, you're good to go. All right, but for that computerized machine, you don't ever lose, even for 5 seconds, you don't lose power because that battery backup will immediately start working. All right, so here's all the components of the high pressure system, of the intermediate pressure system. So you see, with the pipeline pressure coming in here, your gauge is going to read 50, comes through. It can come through a tube through your O2 flush valve that completely bypasses the entire machine. So this would simply be a tube that comes from the wall, runs around the front of the machine. The front of the machine, remember seeing that little green O2 flush valve? It's going to run directly in front of that flush valve and go directly to the patient. Okay, so it never goes to the vaporizer, never goes to your flow meters. Therefore, you can deliver 50 psi or so to a patient, okay, if you're sitting there holding that down. So you never want to flush your O2 whenever you are on ventilator on the inspiratory cycle, or else you can really give a huge amount of volume in just seconds. And those things, they range between machines, but they're going to feed around 35 to 75 liters per minute of O2. Okay, so sit here and hold that flush valve down. It's going to give on average around 50 liters per minute. Okay. All right, so it's not going to kill a patient immediately, of course, because at any one time we're ventilating with, quite a volume, 600 to 1,000 mils. So if you hold it down for a second, you could get about 750 mils or so. All right, but that's also going to your bag. It's filling up the bag. So there's some safety in that. One other thing that you'll be taught to do is that O2 flush valves, you can give it for transtracheal jet ventilation. All right, if all else fails, you have to put in a crike. Then you have no other way to give transtracheal jet ventilation. This machine can't do it. None of our machines can do it. Okay, so the only way you can do it is you either push this, which the manufacturers do not recommend, but that's what you have to do, or some hospitals have a specific outlet for transtracheal jet ventilation in the ORs. Okay, and then you just plug directly into that, and then you're going to have a little device where you just okay, and then you are the jet ventilator. Okay. Okay, so that's important to point out, is that your oxygen flush valve is on the intermediate system, and whatever your house pressure is what's going to be transmitted to the patient if they're hooked up to it, and they're on the inspiratory cycle of the ventilator. Okay, if they're not, if they're spontaneously breathing, Why is it not super imperative that we don't push that valve when they're breathing in? And the answer is because when you're spontaneously breathing, we have the expiratory side open. Okay, the expiratory side is open at that point. So they can exhale at pleasure. They can do whatever they want. So if we push that valve, it's going to immediately spill over into the expiratory limb too. It's just going to go out the scavenger system. It's not going to go to the patient and blow their lungs up. So the bag itself is a reflection of the patient's lung. If you see a bag this big, that's what a patient's lung looks like. Okay? If you see a bag that's completely deflated and there's no air in it at all, that's what a patient's lung looks like. They are directly connected when they're hooked up to the tube and your circuit's hooked up. Okay, so you're spontaneously breathing, your APL valve's all the way open. That means that the expiratory limb is completely open. There's no resistance to it. And anything the patient wants or anything you give is going to go directly out of the expiratory limb. That's why it doesn't matter if you flush when they're spontaneously breathing with an open APL valve. Okay, this is just to correlate the intermediate pressure, showing that here is 50, and it's just hard to see here, but reading 50 on our wall right now, and then over here on your pipeline pressure under oxygen, it's reading 50 as well. Okay, so those should always correlate. Some ORs, when you walk in, you're going to see a digital readout and no longer see these analog pressures. All right, it's just going to be a digital readout. All right, on every single anesthesia machine that you will work with, you're going to have a spot for nitrous and oxygen, but not every single one is going to have a spot for air. So I believe most of them are going to have a place for air, but not all of them. So that's just something our books point out, is it's mandatory for nitrous and for oxygen. All right. And you know, we've talked about that. Have we talked about the DIS system before in this class? Okay, not really, kind of. So just a quick review. The DIS system is the diameter index safety system. That's one that you connect to your house supply and you connect it to your machine. So each of this housing right here, their specific diameter, they can only plug in to their specific gas, and they're color coded. All right, so air is yellow, oxygen's green, nitrous is blue, suction is white. All right, they can only be plugged up to their specific diameter index safety system device. All right, and every single inlet, no matter what you hook up to on this machine, every single inlet where anything is being pushed into the machine, it has to have a check valve on it. So it's got a valve on the inside of that inlet preventing reverse flow. Right? You never want anything coming back out and filling up, say, your O2 tank and diluting it, or filling up your nitrous tank, or going into the house supply. Okay? Okay, oxygen pressure failure devices. So I found this kind of interesting as I was reading that the primary book I use for this equipment lecture is Dr. Dorsch's book, because it's imperative that we teach this, but no class, there's no class geared towards it in any school where you have just an equipment lecture. So we don't have an equipment textbook, and you fit this type of stuff in. All right, so our physics book, of course, doesn't cover it. It talks about pressure, it talks about flow, it'll talk about your breathing systems, but it doesn't talk about the components of this. Nothing really does. All right. So as I was looking at this lecture, it said that that the pressure failure device on here, the thing that's measuring your O2, it doesn't have to alarm until it reaches 19% or less. Well, that's a hypoxic mixture. I found that absolutely ridiculous. So I went to each of the manufacturers' websites and saw that nobody really makes any equipment where it does that, even though the standards would be 19% for this oxygen pressure failure device. The reality is all the machines basically shut off at 25%. So you shouldn't be able to deliver less than 25% O2. Okay? So that's the practical anesthesia machine. About 25%, that means that if you turn nitrous on, you could deliver 75% nitrous, 25% oxygen. If you turned air on, you could deliver 75% air, 25% O2, okay? But you can't get less than that. Okay, this is the O2 sensor here. Let me turn the slide off for a minute. The O2 sensor it's an electrical component that, all right, so it's an electrical component. It's housed in this black device here. It's got this telephone cable that runs through the back of the machine. But this little thing right here, these things are, it's made out of metal. It's got some microcircuitry on it, and you get these things out of the refrigerator. So when you check your anesthesia machine, if it says O2 sensor pressure failure, then, or O2 sensor failure, then you got to go look in your refrigerator and get a new one, okay? So that's the only place they're kept. They're in a package. Get them out, open it up, drop it in here. They just set in there. They don't screw in or anything. They literally just set in the housing, and then this bottom device here, that's what screws in and it holds it down in place, okay? But this O2 sensor is, that is what's doing the job to send the signal to the back of the machine to tell it how much O2 you have. And you can change the alarms on it. You can change the alarms on it to not alarm less than like 30%, but standard is for all of our machines, we make it alarm at 30%, okay? So once it hits 30%, this thing right here is going to start squealing. And it's going to send a signal less than 30%, the machine's going to go off. Okay? We've already talked about the fail-safe valve, but that fail-safe valve is the one that allows nitrous to flow based upon pressure. If it's less than 30, then it's not going to allow any nitrous to flow out internally. All right, so you can't deliver a hypoxic flow. All right. This is the valve itself. Going to ask questions about it. I'm not going to put a picture of this on here. You don't have to know what the components are. We can't even see this. I mean, it's inside the machine. We can't even take the machine apart. Okay. All right. So here on this reference, it says 20. Half of the references I use said 30. So on this, I would just say, since I have it written here, go with 20. If your PSI of O2 falls less than 20, nitrous cannot flow. That would be a more conservative approach. All right, so if it falls less than 20, then you cannot give any nitrous at all. Your threshold has been reached, the valve will close, and nitrous will not flow. Okay. Okay, this is just the same thing, just showing how it flows in and it pushes the valve open. All right, so 5 tasks the oxygen has in the machine, and that is, it's going to move to the flow meter, you turn the flow meter on, whatever you turn it on to, it's going to be delivered to the patient. It's going to power the oxygen flush valve, which bypasses everything else. It's going to be delivered at the intermediate pressure. It activates the fail-safe mechanisms, so that's what causes that fail-safe valve to rise. Activates the oxygen low pressure alarm, so your pressure, your O2 sensor I just showed you, and then it compresses the bellows of mechanical ventilators on most machines currently. The newer computerized machines are able to utilize air. Okay. Okay. So we're going with 20. Okay. So I'm gonna ask you that on a test. All right. But this one here on Dr. Dorsch's book, there's 2 places in it. One said 20 on his pictures. The other says 30 here. Is when it will alarm. All this is saying is that audible, it's going to cause an alarm at 30. But at 20, that's when it's going to shut off the fail-safe valve. Doesn't mean it's going to alarm. Okay? It just shuts it off, and then you can't deliver nitrous anymore. All right. This is really wordy. Anyway, but it all says the same thing. All right, so do you understand what your fail-safe valve is? It's literally one valve. And it does just one thing, prevents a hypoxic flow. Okay? All right. So let's get through this and then we'll take a break. Our O2 flush valve. All right. As you see your cylinders come in, pressure is reduced right here. Your pipeline pressure is supplied here. So no matter what your flush valve gets, it has to be intermediate pressure. You cannot supply this high pressure system to your flush valve because it will go through this pressure reducing valve here. All right, or this pressure reducer here. So your flush valve will always be at the intermediate pressure system. Okay, and this is how oxygen moves through the system. Everything you see in pink or red there is oxygen moving. All right, and here, know this range, 35 to 75 liters per minute. That's a big range, yes, but it's a huge volume no matter if you're looking at 35 or 75 liters. It's a big volume if you were giving that directly to a patient. If you were to push that valve and have your APL valve closed, lungs are going to drastically inflate, cause barotrauma, and dilute your inhaled anesthetic. Okay, so let's say that you're on the ventilator and you have to doesn't matter if you're on the ventilator or not, you're just connected to your circuit. When you bypass your anesthetic here, this is your anesthesia. If you bypass that, it's going to come in, it's going to dilute all this. It's going to provide a huge sum of oxygen with very little of this volatile agent anymore. So you get a dilutional effect. So if you did this repetitively, you're going to drop your anesthesia levels. Okay? You're going to dilute them to a point where you'll see clinically that it will drop on your monitor, and you're going to see your inspired level drop of whatever your volatile agent is. Once that thing drops, once your volatile agent drops, you can get awareness. Okay, so awareness can occur if you're using your flush valve frequently. We shouldn't ever have to use our flush valve frequently. The only time that you would is if you had to do transtracheal jet ventilation. Other than that, we use it simply to fill our bag up. When we're beginning spontaneous breathing, like when we squeeze a bag, if our APL valve was all the way open, it's going to squeeze it all out to the expiratory side. It's going to leave, our bag compresses, and then we have to flush it to expand our bag again. All right, so it's just so we can rapidly fill it up. Okay. Okay, so this is our flush valve. All right, it's just showing where it is. It's located on the front. It's located on the front of every anesthesia machine. Doesn't matter which anesthesia machine you get, you're going to see it. And usually it will even tell you. It'll be a green button and it'll say O2 plus. Okay, O2 plus. That's what it's coded as. All right. But you see that it does bypass everything up top. So all of this is a separate system. This comes in through the wall, through the back of the machine. It's directly piped from that back of the machine directly across. So you've got a small little tube that's going to come across at 50 psi, go directly here to your O2 flush valve. That O2 is going to come out of here. So you see how it's diluting the anesthetic? Because the anesthetic is coming, your O2 is coming through here, bypassing through this vaporizer, comes back across this vaporizer, exits through a tube, comes back across and down. When it comes down, it's going to come over to this common gas outlet right here. So now you got volatile, you got O2, you got nitrous. Now when you flush, it's going to dilute all those right here at this point. Okay, that's why you get your dilutional effect. So now, if you think back to that kind of busy diagram with all the valves and everything, if you can picture three-dimensionally or internally, if you can drop that on top, then your cylinders are right around here. Okay, so you're going to have your cylinder yoke here, tubes that run in. You've got your pressure, your first pressure gauge right here that's reading at O2 2200. Immediately after that, you've got your pressure reduction valve. Okay, so immediately after that, it's going to reduce pressure in this component right here. So you've got your board-on pressure gauge and your first pressure reduction valve right there. Okay, It's where it has to happen because that's where your gauge is. Wherever your gauge is, it's going to be just on the inside. Your pressure reduction valve is going to be just on the inside of your gauge. Okay? Then that gauge, or then your O2 comes in to the back of the machine. Pipeline pressure comes directly into this pipeline pressure gauge, reading at 50. It's going to go through a small little tube, going to be reduced further right up in this area where another pressure reduction valve is, and it's going to feed your flow sensors. Flow sensors then spill over. This is oxygen. Flow sensors are going to spill over, sending oxygen over to your vaporizers. Small tube comes back, down, and out. Okay, out this one little thing here. If this thing was disconnected, there's no way you could give any air at all to the patient. You could give nothing to the patient. So this housing right here, it's crimped. All right, you should never be able to remove it. All right, we should not be able to remove that. But it is made out of rubber. That's a component that could break down over time. So it's something that if you are getting a leak in your system, that's something that you should always check. But if that thing breaks, then our anesthesia machine is going out of service. All right, because we can't replace that. All right. Our anesthesia tech may be able to replace it, but we don't have the tools to replace it inside the OR. Okay? So know your pressures here. To go from intermediate to low, all intermediate pressure is 50. Now we're moving to our low pressure, and I just showed you that. It's located just upstream the flow control valve. So just beneath as your flow sense, or I mean just beneath your flow meter. And you're going to get a reduction to 26 psi for nitrous and 14 for O2. So you need to know that. Okay? And then the purpose is to eliminate fluctuations in pressures applied to the flow indicators caused by fluctuations in pipeline pressure. So you've got these huge cylinders sitting somewhere in the hospital. They're huge. They're sending out, it's not always just a constant pressure at 50. Those things, it's kind of like pulses that can come. And you can't allow those pulses to affect your anesthetic. So it reduces down to a very consistent PSI. So you have a large safety margin. If you're going from 2200 to 50 to 14, huge safety margin so you don't get those pulsatile waves that could come in and potentially disrupt your anesthesia. I don't want to beat a dead horse here, but I know that there's some confusion about the pressure regulators, because one of the diagrams only shows one for nitrous. That's why I mentioned earlier. But the way tests are written, think about the way tests are written. Anybody could ask you, how many pressure valves are present between pipeline pressure and the patient? And how many would you say? One. Okay? So there's a simple diagram showing that with only one pressure regulator. Okay? Now, that's because you're going from 50 psi down to 26. So there's only one that reduces that. Now, if you were asked a question, how many pressure regulators are there between nitrous oxide cylinder and the patient? And the answer is 2, because you must reduce pressure from 2200 to 50 and then from 50 to 26. Okay? So, is that a little more clear? All right, so on this, I just want to show how this fail-safe valve works. All right, so this is the fail-safe valve. All right, so our pressure here is at 745. Pressure here is at 2200. This is 50. This is 50. Okay? So we're not using this. We're not using this under normal circumstances. So here we have nitrous oxide coming in, but it can't enter right now because this is closed. So our O2 molecules are going to come in, and they're going to come up to this point here, and they're going to force this up. But this is a closed diaphragm. So as it presses up with pressure, it's going to cause this to rise. As this rises, this area in between here, all right, so this is your height here, this area is all going to be raised. So this diaphragm now will be up here. And this portion is going to be up here. And it's going to allow nitrous to flow through here. There's no mixture of gases. So then the nitrous is going to flow through. If your PSI is less than 20, then this can't happen. So we get rid of that. So that diaphragm then stays on the bottom of the fail-safe valve, and you can't have any nitrous that flows at all from your cylinder, from your pipeline. It doesn't matter. Okay? So is that a little more clear? Yes? Yeah, we're sticking with 20 for the PSI to it has to be greater than 20 to allow nitrous to flow. It has to be, according to that one paper, less than 30 before the alarm will sound. Okay? So, but we're going for 20 for the pressure. All right? It has to be at a 20 pressure or greater for nitrous to flow. Okay? Then the last thing is, anybody that wants to go next door after lecture, you're more than welcome to, and we can look at the machine directly. I brought it in here before and it never works because the class is big. Everybody tries to gather around and it just doesn't work. Okay, so let's look at this. Right behind here, you have 3 hoses. Okay, you have oxygen, air, and nitrous. Okay, so these are our 3 hoses that come in. This is your pipeline pressure. So this is pipeline. Now these are going to feed in, and when they come in, these things are going to go to your cylinder. Okay? So this is going to immediately feed in, each one of these, into this pressure gauge here. All right? So there's nothing in between other than just a straight hose from your inlet to your pressure gauge. That's why it will read 50. Okay? Now over here, you've got your O2 cylinder. You've got an O2 cylinder pipe that's going to come around. It's going to run directly up here. Here, it's going to read 2200. So there's nothing in between point A and point B. Okay? Can't be because it's reading 2200. But at this point, immediately after this, you're going to have your first pressure reduction valve. All right? So you're going to have a pressure reduction valve just on the back side of this. So it's going to actually lie, if you look at this as a box, this box is this wide. So you have plenty of room behind the machine. Okay? So you're going to have tubes that run out kind of like that. Then you're going to have a valve behind that that reduces the pressure. Okay? So that's done right here. Here, part of your O2 from the cylinder is going to go through a pipe up to that fail-safe valve, okay? And then no matter if it goes to the fail-safe valve or if it goes directly up to your flow meter, it's going to go through another pipe that has a pressure reduction valve that's going to reduce it down to 14, okay? So here, your pressure is 14, okay? Here, your pressure is 26, okay? In your flow meter, okay? Any question? Okay, let's move up down to 44. Okay. So the components of the low pressure system are the flow meters, the vaporizer, check valves, and the common gas outlet. All right. So the only thing about the flow meters are you always read them from the top unless it's a ball. If it's a ball, you read it from the center. But you're going to see that there are multiple types of flow meter, of floats. Okay, multiple types. Every one of them you read from the top except the ball. The ball you read from the middle. All right, this is a diagram of what I explained first, why you put oxygen on the column closest to the vaporizer. If you don't have it that way, if you were to get a break in the tube, then you're going to have some volume of oxygen that's going to leave and never hit the patient. Okay, so all newer vaporizers are like, okay, Draeger and Omeda. Those are common type of vaporizer or common type of anesthesia machines. Okay, always O2 nearest the vaporizer. Okay, now proportioning system is it's a mechanical way, not an electronic way of ensuring that a hypoxic mixture can't occur. So in the flow meters, there's a chain attached to it. So here you have O2, here you have nitrous. You've got a you have a chain attached to those flow meters. At this, I don't care about the 28 and 14 teeth, but what that shows basically is that if oxygen is not flowing, nitrous will shut off. Okay, so there's two ways to ensure oxygen is always flowing to the patient. First, it's a fail-safe valve, and the second is this proportioning system. All right, the proportioning system is where your flow meter is. When you put your hand on it, directly behind your hand, it's a chain that's attached to it. All right, that doesn't allow you cannot turn O2 on greater than 70, or you can't turn nitrous on greater than 75%. Okay, these teeth won't allow you to do that. If you turn it up to 75, oxygen will raise at 25%. So this ensures that you cannot have less than 25% minimum O2 delivered to a patient because of this right here, because of your proportioning system. Okay, so this is a mechanical way, not an electronic way. All right, the electronic way, as we saw in that slide a couple slides ago, showed 19%. That 19% would be a computer-generated number. If it reached 19%, then it would have to raise the O2. This is a mechanical way. So the reality is you cannot deliver on any 100% computerized machine, you cannot deliver less than 25% O2. It's only the computerized machines that you could potentially deliver less than that. Okay? It's just called a link 25 system. It's because it's a chain link that's attached to it, and it ensures 25% minimum oxygen. Okay, it doesn't work if you screw the pipelines up. So if you put the wrong gas on the machine, it doesn't know that. It's simply a mechanical device, okay? So it will not detect anything wrong. If you have defective pneumatics or mechanics, it has to be installed properly. And if you have a leak downstream, so remember this is on the flow meter itself, if they're on the handle of the flow meter, if there's a break in the glass above that, if your vaporizer isn't housed properly, if it isn't seated properly, it doesn't detect any of that. You can always deliver a hypoxic flow from any point nearest the patient from a point that is measured. Okay, so here at the link 25, it's where you turn it on at the rotometer. This is just saying the glass, if it breaks, then the proportioning system is meaningless. All right, your APL valve. So on our Narcomed, this is your APL valve right here. Okay, so this is simply a device that you rotate. On the Narcomed, there's no numbers on it. Okay, so it's all about feel. You got to feel it, you turn it, you see how much pressure you have in your bag. Do you want more or less? Okay, so you can't set it to a specific number. These up here, you'll see these on a lot of the newer machines, and they do have numbers. All right, so it'll say minimum, it'll say spontaneous. Spontaneous means completely 100% open, or it'll give numbers. So 10, 30, 50. All right, these are all numbers that indicate basically a PEEP pressure. So if you set them on 20, then that's the equivalent of 20 a PEEP. Okay, so whenever we're getting people back breathing, they like to breathe against some sort of pressure because we all have an intrinsic PEEP. You know, our intrinsic PEEP is 3 to 5. We breathe against our glottis. That's why we don't develop pulmonary edema all the time. We have a negative pressure system. We like to breathe against pressure. So when you have a tracheal tube in and your epiglottis is no longer working because it's open and you have an open tube, we have to create a system of pressure. All right, so when you're getting people back breathing, you like to set this kind of right in the middle of that minimum and 10. You want to give them 3 to 5 a PEEP, and you give that with the APL valve. Okay, we don't set a number. There's nothing that you push on the machine. You control it with your hand. Okay, so on this machine, there is no number. You simply will control it with your hand, and you'll watch this gauge right here. This is your pressure gauge. This is 10. This is 0. You're going to get them between 3 and 5 or so. Okay, So that's not testable for this, but your APL valve, that's called your pop-off valve. It's on the expiratory limb. So as you're breathing out, you're breathing against your pop-off valve. Okay, if it's completely closed, you cannot exhale anything. All right. It does not work when you're ventilating somebody. All right. It only works if you're spontaneously breathing. Okay. If you're spontaneously breathing, or if you have them on manual, if you're bagging them, then it works. But if you have the ventilator turned on, you told the computer to work, it bypasses this. So this is no longer there. Okay. It's no longer there. It's not even a factor. So you could have it all the way closed and it won't matter. It does not prevent anything from occurring at that point. Okay. Our scavenger. So our scavenger's on the left of the machine. This hose right here, this black hose, that's the only thing that connects the scavenger to the expiratory limb. This is going to come out of the bottom of your CO2 canister. All right, so this is going to be connected down here. Runs in. This handle right here is what turns this thing on. Now, we have to make sure that this thing's on. There's no numbers on this either. You just have a line. And this ball should be floating somewhere in between that line. Okay? So this is your scavenger. This housing here, it's just an empty container. All right? So there's actually nothing in there. There's just some pipes in here that run along, and anyway, it just moves the air along so it doesn't go back into the system. Once it enters this, it's not coming back out. Okay, so you can't breathe against it. You can't. Does that look funny? Sorry. I saw you guys laughing. That was not my intent. Okay. Okay. Well, that didn't help. Okay, there we go. I am not an artist. Okay, so the point is, you have a scavenger system that pulls air out. This is attached to the hospital vacuum supply. Okay, so this here is your hospital vacuum. That's going to run back into either your overhead device, or like in the sim lab, we have them plugged into the wall. Right? And I'm just showing that it is turned on. Okay, if it's not turned on, then the patient's going to rebreathe their exhaled gases, the ones you don't want them to rebreathe. Okay. All right. 5 components. Your collecting device, which is your black hose here. That's your collecting device. Or sorry, this is your transfer tubing. This is your collecting device. Your interface is right here. Your disposal system is the house system. This is the disposal tubing. Okay. So 5 total components. And your interface is what's going to prevent pressure from entering the system and causing trauma to the patient. All right. So this just shows again the 5 components to it. And some of the rules regarding scavenging is that waste products can't be above, or halogenated gases can't be above 2 parts per million. Nitrous can't be above 25. Okay, that's the only things that we have to know is these 2 right here. Okay, now CO2 absorbers. On this Narcomed, you have a dual chamber CO2 absorber here, so we have 2 of them that's set. I took a lot of pictures this morning of this, so I'll show you a lot of pictures. All right, so we use this to prevent CO2 from being rebreathed. All right, so it's going to conserve agent, it's going to conserve your gases, and it's going to conserve humidity. And it only works at low fresh gas flow. So if your fresh gas flow is like a half a liter, 1 liter, 2 liters, then it works. If it's greater than that, at high gas flows, where does your gases go? They're all sucked out the scavenging system. Okay, so you're going to suck everything out at that point. All right, so you don't even give it a chance at that point to go through the CO2 absorber to cause that chemical reaction to absorb the CO2. All right, so it's only going to work at low fresh gas flows. All right, so this is I'll explain this further on the real pictures. All right. So if you were to create an ideal absorber, you'd want something that that's not going to react at all with your volatile agents. You don't want it to react with anything other than CO2. You don't want it to be toxic to a patient. We've had multiple types of CO2 absorbers in the past. Really the only one that's used anymore, there's two of them that's used. One's a soda lime absorber, which is sodium hydroxide. That's a small component, and it's calcium hydroxide. And then something called Amsorb. But until the 90s, we had one that was commonly used called Bear Lime. And Bear Lime had a reaction that occurred when you turned sevoflurane on with it that caused the thing to burn up. I mean, literally, if you touched your hand to it, it would be hundreds of degrees at times. So it gets really, really hot. It's an exothermic reaction that can occur in these. So now there's only two types that are really used, and that's the soda lime and the Amsorb. The low resistance, you measure these granules based upon the size mesh that is on top of it. Okay, so the CO2 cylinders here, this is a mesh. Okay, a mesh is like a colander. It's simply a device that prevents something from falling out of it. So each of these, if you measured per square inch, it would have 4 to 8 openings per square inch. So these are measured in something called mesh. So it's 4 to 8 mesh. That is, everybody asks that question on every exam. All right, so 4 to 8 mesh is where you want these CO2 pellets to be. All right, that prevents low resistance and ensures maximum absorption of CO2. These things are not very expensive. I think they're about $10 or $12 per canister. They're very easy to handle because most of them actually come in a plastic wrap. You simply remove the plastic wrap, you put it on the machine. Okay, the newer ones, they even come with a handle on them. I mean, they're so simple. And you just plug it in, it's plug and go. There are some that will have an open container, and you have big bags of your sodium hydroxide or your soda lime, and you pour it in. Okay, then you pour it into the container, and anyway, we recently had those. I mean, we kind of got rid of all of those probably a year ago. All right, and they're very efficient to absorb CO2. All right, so your goal is you want all CO2 removed from the system. You do not want a patient rebreathing any CO2. You see that on your monitor. So on your monitor, you're going to see end-tidal CO2. That's a value. And then you're going to see inspired CO2 directly below that. That should always read 0. Okay? If it ever reads anything above 0, then you need to start troubleshooting. All right? And this is one of the first places you should start to troubleshoot. Is my CO2 absorber exhausted? Okay? Is it full? Is it desiccated? Is it dry? Okay? So you have calcium hydroxide that's primarily what's causing this reaction. And it's going to neutralize CO2. It's going to produce water. It's going to produce calcium carbonate and heat. All right, so you can fill these at times too, and they do get warm. But the soda lime doesn't have a substantial exothermic reaction. So you fill it, it can be a little bit warm, but it doesn't burn your hand or anything. But the Bear Lime, that thing would literally burn your hand. It would cause entire CO2 canisters to melt at times. That's why they pulled it off. Okay, because patients got hurt. Okay? All right, these canisters, this ring system here, these are called annular rings or baffles. And they create these, and they put these all these devices on it to try to help the flow dissipate evenly. Okay, you want flow to move throughout this evenly. And what can happen with these is they're not packed right, and the flow bypasses the place with the greatest resistance. All right, so you can actually lose a lot of this may never even see CO2. All right, if it's not packed well, or if this flow was directed, say this flow was just directed for some reason at this side, well, all this is going to fill up with CO2, and none of this is going to. All right, so you try to prevent that. So they put these annular rings on, and that tries to dissipate all of the exhaled gases evenly. But the way these things, the way gases move throughout this canister is actually pretty interesting. And gases like to stick on the walls. So whenever you breathe, whenever you exhale, and this thing comes in, gases like to follow the wall and then come down. So the place that you're going to actually see the least amount of absorption is right in the center initially. Okay? So if you didn't have all these rings and you allowed just an open system to come in, then it's going to go throughout the wall. It's going to fill up the system. The whole outside of it's going to turn purple. That's the indicator to show that the CO2 has now absorbed into the pellet. And it'll look as though everything is exhausted in the system. But these rings help dissipate that and help it move central, okay? It helps it move central as well. And whenever you take one of these out of the package, you're supposed to shake it a little bit. All right, shake it. That helps even packing of the entire thing. All right, so this is the most common type of absorbent that we use. This is the cheapest. It's highly effective. This is a good absorber too, but this thing is much more expensive and it doesn't last near as long. This one got X'd out in the mid-90s, okay? But every book, the only reason I showed it is because every book will still talk about bare lime. All of your review books are going to mention bare lime. Every single book that you have is going to mention it, all right? But it's gone, no longer in North America. It is, it's a thing of the past. Okay, so know the components of these. All right, there's a little range based upon the manufacturers, but it's pretty consistent around 80% calcium hydroxide. So the greatest component in soda lime is calcium hydroxide, not sodium hydroxide. I remember as a student, I got that question wrong. I put sodium hydroxide. I remember I got that question wrong. I learned, I got burned because I was never shown a diagram like this, and I thought it's sodium hydroxide. It's soda lime. Surely the most is sodium hydroxide, but it's not. Okay, each of these have a role. This role is to combine with the CO2 and form calcium hydroxide, which is a primary product of this reaction. The water is present to help speed the reaction. Okay, it's going to help. A dry granule doesn't work. You have to have a moist granule. So they have to have water present for this reaction to occur because it starts out with water plus carbon dioxide, forms carbonic acid. Okay? So you have to have it to begin the reaction. All right? And if you see stuff like this, anytime if you see a hardener, that helps that pellet not turn into dust. That's why they put these hardeners in here. And you'll see that throughout your reading and as you study for the C exam and boards and stuff, you're going to see silicas placed in or this calcium sulfate is going to be placed in. And these are simply hardeners to ensure that the pellets don't turn to dust. All right, because that dust is toxic. The patients can't breathe that dust. If they do, you're going to get laryngospasms, bronchospasms, and all kinds of bad juju, okay? So you got to try to prevent it. Okay, so some important numbers here. Each canister of absorbent is going to hold about 1,000 grams of granules. All right, 1,000 grams of granules. Soda lime, 26 liters of carbon dioxide per 100 grams of absorbent. Okay, so make sure you know that. Okay. Calcium hydroxide is 10.2 liters per 100 grams. So looking back here, this one is less effective. You're going to see about 10.2 per 100 grams. And over here, you can have upwards of 26 per 100 grams, okay? All right. Average person under anesthesia is going to produce 12 to 18 liters of CO2 per hour. So if you were running this at low flows and all of the exhaled gases were coming through the CO2 canister, then you could see that it's going to last you all day. Okay? So if you're running this machine constantly for 10 hours, then you would need to replace your CO2 canister. The reality is we don't run it at low flows for 10 hours because we don't do anesthesia for 10 hours straight. It's almost, I've never done a case that's longer than 4 or 5 hours. Surgeries are fast anymore. You can go in and do any type of case anymore in hours. So you're going to provide high flow at the beginning. You're going to provide high flow at the end. That bypasses the system, so it doesn't even count. Low flow is when it's going to go into your CO2 absorber. Okay? But an 8 to 10 hours under full general anesthesia at low flows, that's when you're going to see exhaustion happen of CO2 in about 10 hours. Yes? I have no idea. I have no clue what they do in space. I feel like I'm in space a lot, but no, I don't know. I wish I knew. I know, but Dr. Nolan, he's really into relating space examples. Has he done that for you guys very much? He really talks about. He'll bring that in a lot. I'm sure he could probably answer. I'd be happy to ask him that too. But they have to have some way of. They would have to have something such as that because I don't think they have O2 tanks that. I don't know. The answer is I don't know. I can't. I'm not going to try to rationalize it. Okay. Of course, larger canisters are going to have longer use. So you're going to see multiple types of canisters. The one on the Narcomed, big round canister like this. A lot of CO2 granules. And you have two of them stacked on top of each other. Okay? So lots. You're going to have approximately 2,000 grams of CO2 pellets. But some of the newer machines, you're only going to have one canister. It's going to be a small handheld canister with maybe 500 grams. Maximum 1,000 grams in that canister. Only one of them. There's not dual, but with the newer system, you can actually push a button, disconnect it during anesthesia, and it sends everything to the scavenger. All right? Get you a new one, plug it back up, you're good to go. But the machines that most people use around the country are not the brand new ones because they're really expensive, and all of our older machines work perfect. Okay? With these, if you did start seeing rebreathing of CO2 and you figure out it's my CO2 granules that are exhausted, they're full of CO2, it's no longer working, you cannot change it during the case. You drop that CO2 canister, you lose all volume in your circuit. Okay, so that is part of the pressurized system. So you can't do that. But the larger canisters, you're going to use them a lot. You can use them much longer because they have a lot more granules in them. We've already talked about the high fresh gas flows, and you'll see a lot talking about low flows. All right, people use low flows everywhere, all over the country, because it does save a lot of money. All right, it saves a lot of money in terms of the amount of volatile agent that's used. But we're going to teach you here that you don't use low flows in short cases. We use high flows in short cases. We're talking cases that are greater than 30 minutes here. That's when you're worried about your CO2. Okay? All right. So we've already talked about showed you the picture. Make sure you know this. Know this for sure. Know the larger granules. You're going to have smaller surface area. That's why 4 to 8 mesh that's the picture perfect point. That's going to help with resistance. If you did create a smaller granule, which increases surface area, you're going to increase resistance to breathing. Okay, because everything that goes in that they're going to pull against, it's going to increase work of breathing for somebody that's at times recovering from paralysis, and it's too difficult for them to overcome any resistance. So through time, the companies and the researchers have figured that this 4 to 8 is the perfect balance between granule size and surface area, maximum absorption of CO2, and minimal resistance. All right? And then the small amount of water, that 15% of water or so, is added to prevent drying out. The water combines with CO2. And then the sodium hydroxide is added to speed the reaction. And then any hardener, silica, or that calcium sulfate is added for hardness. Okay. The indicator that's added is called ethyl violet. Indicator turns the CO2 granule from white to purple. When it turns purple, that means that granule that you see as purple, it can no longer absorb CO2. All right, it's fully exhausted. So the terms that you need to be familiar with are dry, exhausted, desiccate. Okay, if you hear any of those, it all means the same thing, that the CO2 granule is no longer usable. Okay, important things to know about this, the indicator is it can turn purple when it's under fluorescent light. Okay, it takes a while, but it can still turn purple under fluorescent light. So keep that in mind. If you ever if you're ever worried about the CO2 absorbent not being functional, then you need to change it. Okay, it's going to turn purple when the pH is less than 10.3. So of course, your calcium carbonate and your sodium hydroxide, they're bases. So this is a very basic, this CO2 absorber. It is extremely basic and it's caustic. So if you touch it to your bare hand, it's going to dry your bare hand out really, really fast. And anytime you change these, you should be wearing gloves. You should, it's recommended that you wear a mask and you even wear goggles. But you definitely need to wear gloves because the reality is you're going to touch it. You're not going to go wash your hands immediately. Then you're going to touch your face and your eyes and everything. And you will get dry eyes really fast. I've done it. I promise. All right? The color can revert back to white at times. So it doesn't revert. If you have a completely purple CO2 canister, it's not going to turn back white. Okay? But if you have one that's beginning to turn purple, it's kind of a light shade of purple, you come in the next morning, it could be more white than it was when you left. Okay? That doesn't mean that that it's still good to go. All right? But you can get some slight reactivation over time. More moisture is added. All right? The more moisture that's added, the more this thing's functional. But once you see that thing start turning purple, you need to get rid of it. Okay? So once that thing's about 2/3 of the way purple, you better shed it and get a brand new one. Okay? All right. No more than 1 week. And, okay, so I'm glad you brought that up. How long do they last? No more than 1 week, period. If you put it in a brand new machine, you haven't used the machine at all. The week comes and goes, no patient ever saw that machine. The next Monday morning, you should change it, okay? Because it still loses the moisture. It still can dry out, okay? So you never know for sure. If this thing is dry, it's not going to turn purple. It only turns purple when it reacts with CO2. Okay, if it's dry, you don't know. And then, anyway, we're setting our patients up to rebreathe CO2 at that point. All right, the airspace is about 50% total volume. Two types of airspace, the void and the pore space. The void space is everything in between the granules, and the pore space is actually in the granules itself. And the last statement is just, as you replace it, shake it up. All right, so shake it and then put it in. All right, we've talked about the channeling. Channeling effect is when there's preferential movement of air through the CO2. So it's going to exhaust just certain channels around the CO2 canister rather than from top to bottom equally. All right, we want equal spread. That's why they now try to prevent that, and you need to shake it. Okay. The inside edge of the canister is a lower resistance. So around the actual walls is a lower resistance. That's why they have to put the annular rings in. All right, so here's the reaction. Make sure that you know this reaction too. It's just, this is CO2 plus water equals carbonic acid. Then that carbonic acid is going to be sped. This reaction is going to speed up with the presence of sodium hydroxide. Sodium hydroxide forms sodium carbonate and water and heat. Then that sodium carbonate is going to combine with the calcium hydroxide to form calcium carbonate and sodium hydroxide. Okay, so your ultimate goal or the primary product is calcium carbonate. All right. And remember again, a pH less than 10.3, that's the number for every type of CO2 absorbent. Less than 10.3 is going to turn purple in the presence of CO2. It does not turn purple unless it's exposed to CO2. So if it is dry, it will be white, and then it just won't absorb CO2. Okay? So here's what it looks like. All right, and it is this color purple. It is that clear. All right, it's not a matter of is it purple or is it not. It either is or it isn't. Okay? So at this point, That top canister, it's about 2/3 of the way. That would need to be replaced at that point. Now, with the Narcomed has two, let me see if I have it. The Narcomed has two CO2 absorbers that set on top of each other. This allows a complete path of air to go in between the entire CO2 absorbent. They are both functional, okay? So this air will come all the way through this, all the way down. This is not closed off, all right? It's open. So when you replace one, you have to replace both, okay? However, some policies, some places that you go to work will say, if you're using one as a dual canister system, if you replace the top one and it's still in the middle of the week, all right, it's not Monday morning, then you're going to elevate this one to the top and you're simply going to replace the bottom one. Okay, and that's acceptable. But on Monday morning, you get rid of both of them and you put two brand new ones in. Okay? All right. So not much to talk about with Amsorb. I've never used it. I've never even seen it. It's much more expensive. The primary reason that people use this is that it cannot produce carbon monoxide or compound A. Have you talked about compound A at all? Well, okay, so Dr. Cook, he came in and he gave you that brief history lesson about anesthesia history, and he talked about somebody that killed a bunch of rats with sevoflurane, right? Well, that was him, and it was because of compound A, okay? So compound A was formed, and these rats died. It causes liver or hepato and renal toxicity. Never been shown to happen in a person. But because it happened in rats, thanks to him, a long time ago, that is like a big warning that comes out with sevoflurane. And so compound A can occur with soda lime granules when flows are really low. Okay? So this happens with Sevo when flows, fresh gas flows, are less than 2 liters. Okay? Only at low flows. If your flows are greater than 2 liters per minute, then there's really no chance of it happening. All right? But Amsorb, it completely prevents that from ever potentially happening. So it doesn't happen. Okay? And it really has carbon monoxide is formed at such a minimal amount that it's not even relevant either. And with soda lime, carbon monoxide can be formed. Okay? So if you had a desiccated soda lime canister and they start rebreathing carbon dioxide, well, guess what? You're probably going to see a patient rebreathing carbon monoxide as well, okay, because that's a byproduct that can happen. All right. It also is safer because it reduces the possibility of fire. It's not going to be, you're really not going to have an exothermic reaction that's going to occur. But you saw earlier that it's not very absorbable. I mean, you're only going to get, what, 10.6 or something compared to 26 of soda lime, and it's much more expensive. I think it's like 3 times the cost. So I've never seen it. I don't know anybody that uses it, but I would expect anytime you see people that use products like that, it's because they had a bad outcome on a patient related to something. I mean, and that's when they switch over. Okay. Oh, well, this here, I just talked about what I talked about, so we can keep moving on. All right. Know this too. Okay? So with your CO2 absorber, carbon monoxide can form with soda lime particularly. It generally doesn't, all right? But if you did have a desiccated CO2 absorber, or if you had an anesthesia machine that sat in a room for weeks and nobody used it and you didn't think to change it, then you could see some carbon monoxide form. It's always going to be greatest with desflurane. All right, so this is actually going to produce at a rate that's much, much, much greater than ISO. ISO produces more carbon monoxide than Sevo. And then sevoflurane and halothane produce carbon monoxide at the same rate, but these are very, very low. All right, so very minimal amounts, minimal CO under any circumstance. This one, however, you could get large amounts of carbon monoxide with a desiccated CO2 absorber. Okay. All right. So real quick, some of the early clinical signs that you will notice when your CO2 absorber is completely exhausted. You'll start to see a rise in end-tidal CO2, of course. So you're running people at 32. That's a good place. We like people who are under general anesthesia, 32, 33. You start seeing them go to 37, 38, 42, and you have no reason for it. You don't have any idea why. You start going through your differential diagnosis. You're going to learn all the different things that can happen, why CO2 increases. But right now, this is one reason why CO2 can increase. Okay, so you troubleshoot this. Is it my CO2? Of course, anytime you increase your CO2 levels in the body, you can get acidotic. If a patient was spontaneously breathing, they would begin hyperventilating to try to blow off more CO2. They can get very flushed. You can get some cardiac irregularities. They can definitely begin to sweat, and you will see that. They'll just become drenched. Increased bleeding at the surgical site, and of course, the CO2 granules can turn purple. Late signs are a change in heart rate, change in blood pressure, and then significant cardiac dysrhythmias. All right, so to change this thing, you're going to pull this handle out. Okay, you're going to pull it out, not towards you or away from you. It goes out. That's going to drop this entire unit down. All right, it opens the entire unit up, so the system's no longer pressurized. You cannot provide any ventilation at all to a patient. Dust occurs. All right, this thing is wrapped in plastic whenever you first get it. When you rip that plastic open, you're going to see it's dusty. All right, this dust travels down, and it's caught in this dust trap right here. All right, this dust trap needs to be occasionally cleaned. Do we clean it? No. Anesthesia techs can clean it, but that's not something that we do. So you want to change it on Monday mornings. You want to change it if the color is purple. You want to change it if it's been within a week. Pull this thing open, take the CO2 canisters out, and remove the plastic. I've actually seen somebody that accidentally put a CO2 canister in with the plastic on. All right? If the plastic's on, what happens to your circuit? It's a complete occlusion of the circuit. There is no air movement that can occur. Okay? So you must remove the plastic. Keep that in mind for simulation purposes. When we have you guys come over next semester for your anesthesia management and we're troubleshooting the anesthesia machine, I guarantee you I'm going to do that. It's gonna happen. So when you start seeing, I can't ventilate, check your CO2. All right, see if that was a problem. Insert the new canister on bottom and the old canister. So if with that dual chamber system, you bring the bottom one to top and you put the new one on bottom. Okay, and you keep them rotating like that. So you're always going to change the top one and throw it away, move the bottom from the top, and put the new one on bottom. All right, then you're going to retighten this, simply move it back, and then check the breathing circuit for leaks. Now, this is imperative. You always have to check for leaks. Now, I'll explain what that is next semester when you come in and you do your machine checks. But anytime you do anything in this machine, you need to recheck it. And this is a frequent thing that happens. These things set in a housing that sits around here, right? So they fit in. Sometimes they can be slightly off center, and you clamp that thing down, and there's a break in the seal, all right? If there's a break in that seal, you're not going to be able to ventilate the patient. You lose pressure, all right? So the pressure comes pouring out of here now, and it doesn't go up to the patient. So if you ever don't... This happened recently. Somebody changed the CO2, didn't do a leak test right after, brought the patient in. Patient's laying there, and they cannot get any volume at all to the patient. Well, it's because that was the first thing I checked, was this. What'd you do last? And I don't know. And then, did you change the CO2? Yes. They changed the CO2 in between cases. Simply, I opened it up, rehoused it, and closed it, and that fixed the problem. Okay, because the gas leaks, you can't ventilate a patient at that point. Let's see. Okay, This is the newer type on the Apollo that you'll see. This thing is, it comes just like that, okay? So you can get some that come with the handle on it or with this one. This actually just houses a canister that sits down in this. So you'll simply pull off the top of it at that point, drop it in, and just plug it. But with this one, you can change this in the middle of a case. And you will not lose pressure in the system, okay? All right. Yep. I'm fixing to ask you that. She said, Susan just said, what happens in the middle of a case? What would you do if you realize that you need to change your CO2 canister? All right? So I'm asking you that basically right now. What would you do intraoperatively if hypercarbia occurred due to exhausted CO2 absorber? You say it changed the canister. You can only change the canister with this type of machine. Okay? But in the standard workhorse machine, you can't change it. No, you don't have to bag the patient. The patient's on the ventilator. Okay? So what do? Increase your fresh gas flows. That's all you have to do to bypass it. Okay? Increase your fresh gas flows. All right? It's usually recommended to be above 4 liters per minute to ensure that it doesn't go to the CO2 absorber. At that point, it bypasses everything that you give to the patient. All volatile, all oxygen, all nitrous is all going to be exhaled. But at that point, you got to get your fresh gas flow up since they're not rebreathing, right? Rebreathing is what keeps the volume in the circuit. Since they're no longer doing that, you have to ensure that your fresh gas flow is about minute ventilation. So if they're breathing 10 times a minute at a volume of 600, that's a minute ventilation of 6 liters, then you need to turn your flows up to 6 liters, right? To ensure that no rebreathing is occurring. All right? Questions? All right, anybody that wants to go look at the machine, you're more than welcome to. I definitely prefer that everybody doesn't come over, so you can come as you want to, though.